how did you begin this problem? What's the very first thing? Yes. Right, subtract 28x. Okay. So that gives me x to the 4 minus 7x cubed plus 4x squared minus 28x equals 0. All right. Now, in my professional opinion, you should always check for what first before factoring a GCF. What is a GCF here? An x, right? However, most of my students all day have not been doing that. So I'm going to do the way most of the students have been doing because they've been getting stuck at a certain point. And we'll talk about what to do when you get to that point and you're stuck, okay? So most of my students today have just been grouping straight off. And they've been doing that successfully. They're taking a GCF out of the first group as x cubed, leaving me with x minus 7. The second group, the GCF is 4x, leaving you x. Okay, hold on. Let me just redo that whole thing. 4x, leaving you x minus 7. And then they've been doing the next step correctly, taking the x minus 7 out of each group. That's what they have in common. And then the leftovers are x cubed plus 4x. And they're still doing the next step correct. They say, okay, I have these two factors equal to 0. I can set them both equal to 0. And then this is where everybody gets stuck. This one's fine, x equals 7. But on this one, you get stuck because there's really nothing you can do. You could subtract the 4x over, but then what are you going to do? You can't really square root both sides. Your cube root doesn't get you anything. What you have to notice right here is, what did I come around your desks and tell some of you? What else can you do here? You're actually not fully factored. Pull out a GCF. What's the GCF here? X. The same x we could have taken out at the very beginning of the problem. We'll just have to recognize now that to take it out. So at some point, you're going to have to reckon with the x, okay? And if you did it this way, this is that point. So x times x squared plus 4 equals 0. And then set that factor equal to 0 and solve, but it's already solved, right? It's all by itself. Once you set it equal to 0, it's done. And let me sort of give you a heads up of something I've been seeing students do, and it's getting them the wrong answer. They're trying to save time. I'm going to put this in blue and then erase it because I actually don't want you doing this. Right here, they'll say, oh, I'm going to have to square root. So let me just square root this and square root this. And they say, okay, x equals positive and negative 2. But that's bad math. So if you're going to do shortcuts, be careful that you're still doing the intention of the process, which is this. This should be set equal to 0. And then you move the 4 over by subtracting it. And now you can square root. And this gives you a different answer. It gives you positive negative 2i. So how many solutions is that? 4, and that's what we were looking for. Okay. Raise your hand if you recognize this problem. Where did you see this problem before? On your homework, children. Speaking of homework, are there homework questions? Probably not. Probably not. Any concerns about the homework? If you did not get to the homework, it is in your Google Classroom. I suggest you remedy that situation as quickly as possible because we have a quiz on Tuesday, and it's over yesterday's and today's lesson. All right, so you want to be able to be familiar with those problems. I don't know, maybe even particularly stuff like this where you have to do the square root twice. Might want to freshen up on that and all the other kinds. So no questions about homework? All right. Yes? Number 13? Number 13, is that on the front? Okay, 13. Is there a particular point that you're stuck on? Or do you want me to start from the beginning? Did you understand the GCF part? that I pulled a 2x squared out. Are you good with that? Yeah? So 2 is the biggest number that goes into 2 and 16. X squared is the most they have in common. So we divide that out of both terms. So then 2x squared, what's left over there is an x squared, and what's left over from the second term is a minus 8. And then I set that first factor equal to 0 here, and solve. Oh, I think I know what you're talking about. Are you talking about the 0, or how there's only 3 solutions right here, when we're really looking for 4? So I had a few people ask me about that yesterday, and that was a good question. If you noticed, when you did your homework, the degree is 4, so we need 4 solutions. But how many does it look like I've written here? 3, right? 2 here and 1 0. But the thing about that 0 is it's a double solution because of that squared. I wouldn't count off if you put plus or minus 0, but 0 is neither positive or negative. And when we do graphing in the spring, what that is called, it's just a double root. And that's when a graph will bounce at a root instead of passing through. This is when it's a solution to a quadratic or an even number degree, and this is when it's a solution to an odd number. So really there's 2 solutions right there on the 0, which is what I'm trying to say. It's just obscured a little bit because 0 is neither positive nor negative. It's neutral. Any other questions? Okay, let's begin the notes. All right. Didn't I give you one? All right. What we are talking about today is solving rational equations. So by the end of the lesson, you should be able to solve something like this. Raise your hand if you right now cold can remember how to do this. Cold? Yeah, cold. Like right now, cold. Exactly. Who could remember? Who's pretty sure they'll remember after the lesson? Because you've all seen this before. Okay. So rational equations are stuff that looks like fractions, right? When we classified rational numbers, that was the definition, anything that can be a fraction. And so rational equations are a fraction form, but not like this one. This is a linear equation. It's got fractions, but that's not why, or that's not what we're talking about today. These are called, have a nice weekend. These are called rational equations because they're fractions, but specifically because the variables are in the denominators. And so that's what we call rational equations. This problem right here isn't really the kind of problems we're doing today. It's just a little like sample problem, and the method I use here will be the same basic method that we're going to use for these kinds. So while I'm working this problem, you might be thinking to yourself, why is she doing it like that? I would not do it like that. That's okay. Just breathe and roll with it, okay? Because I'm going to sort of, as we go to the ones with the x's, I'm going to be using this problem to sort of say, hey, it's like that step over there, or like that step we did in the warm-up, okay? One way of solving this problem right here is to figure out a least common denominator, and then you multiply the tops and bottoms by whatever you need for the fractions to match, right? Just like if you were adding or subtracting fractions. And so the first step is to figure out a common denominator for 7 and 3 and 2. Can you think of any number that would be common for 7, 3, and 2? 42. Very good. And also I have to ask, has anybody ever read Hitchhiker's Guide to the Galaxy? Anybody? Children. It's a great book, and it's a funny book, and it's probably just for nerdy people like me, but the whole book, they're trying to build this machine, and it's going to give them the answer to the universe and everything, and at the very end, it just tells them 42. Anyway, it's pretty funny. You should read it. It's a classic. But, well, that's true. Actually, that's true. I did just take it all away. But I mean, it's pretty much part of common culture. I mean, like our common popular culture. So I didn't really give anything away. Gosh, now I have guilt. Okay, so the LCD is 42. Because you were going to read it, right? Yes, I was. Okay. So 42. What do we have to multiply the first fraction by? So the bottom is 42. 6, all right, top and bottom. What about the second fraction? 3 times what is 42? How many times does 3 go into 4? 1, with a remainder of 1, so that makes 12, and 3 times 4 is 12. It's the common denominator. It's a number that all three of these go into at the same time. The 7, the 3, and the 2. Yeah, so this 6 is what I have to multiply 7 by to get 42. 3 times 14 is 42. And then on the last one, what do I need to multiply by to get 42? 21, top and bottom. And so here's where the method comes in for today. I'm not actually going to do this math right now. Like I could multiply across the top and bottom and get 30 over 42x. I could get 28 over 42. I could get 42 over 42. I could combine like terms, move stuff to the other side, and solve. But I'm not gonna. What I'm going to do instead is this process. Because this is an equation and it's balanced, and because all of my denominators are now equal, right? They are all 42. If the bottoms are equal, the tops are equal. So I can just drop off the bottoms, clear the denominators, and just do the math on the numerators. And that's a much easier equation to work with than if we kept them all in fraction form. And what allows us to do that is the fact that it's an equation. If this was just two fractions I was adding, I wouldn't be dropping off any denominators. I would be adding them together. And so then if you just did that math, you have 30x minus 28 is 21. And you would add 28 to both sides, giving you 30x equals 49. And then you would divide both sides by 30, and you'd have 49 over 30. And that's way less of a headache than keeping all the fractions. You drop them off. That's right. And that's the basic process for what we're doing today. Finding the LCD is going to be the hardest work for the lesson, the common denominator. Does anybody need this up anymore? Okay. And I actually decided at the last minute today to present it like this year, so there's some of your notes we need to change. They're currently outdated. I just didn't make the decision before I had made the copies. Are we good on this? Okay, so now we're going to get into how to do that process for the equations with x's in the bottom. Please find this part of your notes and highlight it, underline it, box it, square it, stars, happy faces, Christmas trees, whatever you need to do. This is the main work for today. Factor the denominators first, and then build the LCD from those factors. The least common denominator. So factor all the denominators first using whatever skills we have for factoring. We have GCF, we have swing method. GCF and swing will be the main ones that we use for today and for Monday. And then on this part of your notes, the steps, scratch out number 3. We're not going to distribute and combine like terms. We are going to drop the denominators, okay? So scratch out step 3 and replace it with drop the denominators. Does anybody need that up anymore? So here's how this will look for this problem. You have to look at each denominator individually and see if you can factor it. What do you feel about this first one, m? Can that be factored? No. Right. Oh, and by the way, let's review real quick. We've been using that word factor a lot, like repeatedly. And when that happens, you sometimes lose the idea behind the word. The word factor means to break something up into factors, which are things that are multiplied by each other. So for example, if I rewrote 6 as 2 times 3, those are factors, 2 times 3. If I had 6x squared and broke it up as 2 times 3 times x, that's factors, all stuff that's being multiplied. Okay? So, and I bring that up because if you look at the second denominator, that cannot be factored. Factors mean you're multiplying everything. But that m and that 1 are not being multiplied. What are they being? Subtracted. So in that case, you really can't factor the m minus 1. You could check for a GCF, but they don't have a GCF. So that one cannot be factored. But I have students a lot of times want to try and say, oh, it's m times negative 1. They just sort of break it up. But that's not what it is, because those are different things. So this cannot be factored. This cannot be factored. But this can. This is a GCF problem. What do they have in common? M. So even though it has a minus, and I said here that it can be factored, doesn't mean the minus doesn't necessarily mean it can't be done anything to it. This one has GCF, so it's m times, and then what's left inside. After you divide m out, what do you have? Minus 1. Okay. So we just factored it. So then, going back to that highlighted part, factor denominators first. Okay, we did that. And then build the LCD from those factors. So this is the step where in the warm-up, our LCD was 42, the answer to the universe and everything, right? But here, how we're going to find our LCD is we're going to build it from each of those denominators. Each part has to be represented in the common denominator. Okay? So they're going to form a common one. So I'm going to start by just looking at the first one. That's m. It has to be included in my new denominator, so I'm going to write it down, m. So I'm building this piece by piece. And then the second denominator is a group. It's m minus 1. That also has to be in my common denominator. So then when we look at the last denominator, this needs to be represented in my LCD, and it already is. So I don't need to write it again. Bye. Have a nice weekend. M minus 1 needs to be in my common denominator, but it already is. So I don't need to write it again. Technically, you could write them again, but the problem will get really big and nasty and hard to work with. So don't. Just save yourself some trouble. So now here's my LCD. So just like in the warm-up now, the stuff I had put in red, like what do you have to multiply the bottom and the top by so that they're all common fractions? We're going to do that process here. What's missing in that first denominator so that it will look like the common denominator? M minus 1, right? So it already has the m, but what else does it need? The m minus 1 here. On the bottom and the top. What does the second denominator need added to it? The second denominator has m minus 1, but it needs what for the common denominator? Let me say the question again. It needs m. So it has an m minus 1. It needs an m. And what does that last denominator need to look like this yellow one? Nothing. So just leave it. Just leave it alone. So here we've set it up so that the denominators are all currently the same. They're all m times m minus 1. M times m minus 1. M times m minus 1. So now that they're all the same, we're going to do what with them? Drop them. And we'll just do the math on the numerators now. We have m minus 1 times 2 minus 1 times m equals 4. So you do your math, and I'm going to do my math. Who got 6? Okay. We can't just stop, though. Please read your step 5 with your eyeballs and put it in your brain. Read step 5 to yourself. Step 5 says exclude extraneous solutions that make a denominator equal 0. So you cannot divide by 0. It is undefined. It will not work. So what you have to do is double check that this will work in the original equation. So you go back and you look at all your original denominators and you check them. So checking the denominators. If I put 6 in to the first denominator for m, does it make it 0? No, right? Because it's 6. So that denominator checks. If I put 6 into the second denominator, it gives me 6 minus 1. Like, I don't even actually care what that answer is. I just care that it's not 0. Nice. Do you need me? What? Why aren't you working? Oh, there. Oh my gosh. Good luck. Hey, at least you didn't teach algebra 2 all period. At least you didn't teach the wrong prep all period. All right. So 6 minus 1, not 0. Check. And then for that last denominator, 6 squared minus 6. Again, I don't actually care what the answer is. I just care if it's 0 or not. Is 6 squared minus 6 going to give me 0? No. So it checks. So that answer is good to go. Yes.
Are we ever going to get a problem that does give us 0?
Yes. But I don't remember if it's this unit or later when we're doing graphing and factoring denominators. I don't recall if Monday's homework has 0 in it.
Okay.
Right. Okay, so that's a wonderful question. Thank you. If it does equal 0, if it makes any of the, that's called an extraneous solution, you just cross it out. It's not an answer because it wouldn't work. Okay. All right, next one. You need to think about for a second how to take 2y minus 3 and 3y minus 5 and make a common denominator with those two things. 2y minus 3, 3y minus 5, and how you would make a common denominator. Raise your hand when you feel like you know what that could be. Yeah, okay, thank you. No. Well, what's the first thing you're checking for? Or what's your first step? Like the actual step 1 on your paper. Starts with what word? It's an F word, but it's classroom appropriate. What? Factor, right? So you want to think about, can you factor those? Can you do GCF? Can you do swing method? What do you think? it. So when you thought about GCF method, what'd you come up with? Do any of those have GCF? 30. So 30 is an excellent number if I only had a 2 and a 3 and a 5. But I have the variables in there. And so 30 wouldn't represent the y parts of them. So their common denominator has to represent everything in the individual denominators. And since you can't factor, those are going to be your factors. So in order for your LCD to represent both of those things, it just looks like this. That's it. They can't be factored. Yes. Because we're trying to find one denominator that covers both of the individual denominators. And so that one includes both of them. Just the same way, like in the warm-up problem, we were trying to make all the denominators the same. So 7 times 3 times 2, 42. Right? Same thing here, only instead of 7, 3, and 2, we have 2y minus 3 and 3y minus 5. Multiply them together, that's a common denominator. So on the left-hand side, it has a 2y minus 3. What I need to multiply the bottom by, so it looks like the common denominator, the group denominator. Yeah, 3y minus 5 on the top and bottom. And what about the right-hand side? What does it need? 2y minus 3. So now the denominators are the same. So we drop them off. So now I have 3y minus 5 times 4 equals 7 times 2y minus 3. And if you notice, if you had cross-multiplied on the original problem, you'd be at this step right now. 3y minus 5 is 4, 2y minus 3, or not, times 4, 2y minus 3 times 7. But the only reason we did this is to practice the method. Okay, so you solved that equation. So now it's easy to solve. Because there's no more denominators. We cleared them. And please raise your hand when you have an answer. Thank you, thank you, thank you, thank you. Thank you. Who got 1/2? Okay, excellent. Who checked the denominators with their solution? Considerably less hands. Don't forget to check. I'm checking that it doesn't make any of the denominators 0. So if I'm checking them, when I plug it into the original first one, that's 2 times 1/2 minus 3. Does not equal 0. It's just 1 minus 3. And then in the second one, 3/2 minus 5. Again, I don't actually care what the answer is. I just care if it's equal to 0 or not, and it's not. So that checks. So we can keep that answer. Okay. Oh my gosh, and then we have one more problem. We're going to do it. I'm digging deep. You can dig deep. I'm digging way deep. I really needed it to be Saturday already today. All right. Does anybody need that up anymore? This one, any questions on that? Okay, last one. Step 1 is factor the denominators. These aren't really hard though. Only one can actually be factored. Which one do you think? Only one can be broken down anymore. The x squared, right? How would you break x squared into something times something? X times x. Okay. These are already something times something. 5 times x, 2 times x. And so our LCD, because remember we're trying to find common denominators, because these are fractions with different denominators. We need them to have the same, all of them with the same. So the 5x needs to be part of the new denominator, because it has to be represented. The 2x, I need the 2 in the denominator. I need this x here, but I already have an x there, so I don't need to write that again. And then on that last one, it seems a little bit different, because if I'm looking at the x's separately, okay, I get to the first one, says x. I need that represented in my denominator, but I already have an x in the common one. However, this is a whole separate second x. So I need a whole separate second x in my LCD, right? So the reason why I'm repeating those two x's is because there was double x's over here. Right? So there are times when you'll have something repeated in the LCD, but only if it's repeated in the original problem, right? And so now we multiply our tops and bottoms by whatever's missing. For the first denominator, what is it missing from the LCD? 2x, okay? Top and bottom. What is the second denominator missing from the LCD? 5x, so top and bottom. Where? From the LCD? You mean here? This one? What about it? What about it? So that x is right here. See how I have two x's and a 2 and a 5? And then what is this one missing? 5 and 2, which is 10. All right. So denominators are all the same now. Drop them. I have 6x minus 5x equals 10. X equals 10. Does that make any of the denominators 0? 5x, 2x, x squared? No. So we're done.